Hello, I'm Subodh Kulkarni, President and CEO of CyberOptics Corporation. Today my talk is titled High Precision 3D Sensing for Semiconductor Bump Height Uniformity Measurement Before Photoresist Strip. The agenda for the talk is as follows. I'll talk about the challenges of the traditional method for measuring uniformity after copper plating. Then I'll talk about 3D fringe projection technology and specifically our NanoResolution MRS sensor, which is a type of a fringe projection technology sensor, and specifically the WX3000 inspection and metrology system that uses our NanoResolution sensor. Then I'll talk about bump height uniformity case study findings, the technological roadmap for our sensor and our inspection system, and summarize my talk. First, let's talk about the challenges of the traditional method of measuring uniformity after copper plating. This chart shows the copper pillar bump process flow. You'd start with wafers, you do incoming wafer cleaning, then you define a lithographic pattern where the bump is supposed to go. You do a thin layer of titanium copper sputtering, then you have a lithographic definition, and then you would use the lithographic pattern to grow the copper pillar. On top of it, you could do the solder bump, then you do the photoresist strip, you do the micro bump etching, and then you do the reflow, the solder cap. The typical method measures bump only after all three layers are finished and the photoresist is stripped. The challenge with that is, if the only time you find out that there is a problem with the uniformity of plating, it's after the photoresist has been stripped. And by that time, it's too late to do anything about it. If the thickness is not enough, it would be significantly better if you knew before the photoresist has been stripped. That's what this presentation is about. How can we measure the copper before the photoresist is stripped? So in case if there's a problem, you can have a chance to go back and fix it. Before we get into the exact details, let's first talk about 3D fringe projection technology, which is what we are using to do the measurements here. In 3D fringe projection technology, simply put, you have a digital projector and a digital camera at an angle with respect to each other. You are putting down fringes of light, as is shown here, with a VLSI step height standard, and then you're looking at the fringes from an angled camera. If you look closely at those fringes, at high magnification, you can see what is happening. Essentially, there is a subtle phase shift in the fringes when it goes over a step height. And that's what we are trying to measure, exactly the height. But the way the physics works out, the height gets convoluted with two other variables, reflectivity of the surface, as well as the modulation, the fringe contrast. And the equation is shown here, where you are looking at the intensity of light with the camera. You know the intensity of light you are putting down, but it gets convoluted with R, the reflectivity, the phase itself, the height, and the modulation, the fringe contrast. So essentially, you have three unknowns that you are trying to solve, and that's why you need three measurements at every point. So essentially, three unknowns, three equations. Let's talk a little bit about CyberOptics MRS, multi-reflection suppression technology. We use sophisticated algorithms to eliminate reflection-based distortions. Light tends to reflect, and that's what creates noise. By using sophisticated algorithms, we can eliminate or minimize the noise and therefore generate better images and better measurement. In this case, the pictures speak 1,000 words. On the left-hand side, you have an image without the multi-reflection suppression, or MRS as we call it. And on the right-hand side, the image shows when the MRS sophisticated algorithms are turned on. And you can see the improvement in the image quality with the MRS algorithms. And that's really what we use to generate extremely high-quality images. So what are the advantages and benefits of 3D fringe projection technology? You have an unparalleled combination of speed and accuracy. There are technologies that can give you higher speed, but far less accuracy. There are some technologies that can give you higher accuracy, but far less speed. It's the combination of accuracy and speed that is the key benefit of 3D fringe projection technology, and specifically CyberOptics MRS technology. In this case, we are generating greater than 200 million 3D data points per second. The technology is scalable to 1.5 micron lateral and 25 nanometer vertical resolution. The key is it's capable of generating both 3D and 2D in metrology and inspection in a single pass. We have used our MRS 3D fringe projection technology in many different applications now over the last few years. We started with SMT applications like the classic printed circuit board inspection and metrology. We went into mini micro LED kind of inspections, printer cartridge, very industrial kind of applications like printer cartridge inspection. We partnered with KLA ICOS unit for back-end semiconductor IC packaging inspection. Here we are talking about wafer level copper bump pillar inspection. We have also done it for final vision inspection of memory modules. Additional applications we are looking at inspecting C4 bumps on substrates with significantly higher throughput, as well as in this specific case, measuring photoresist strip thickness and bump height uniformity during the bumping process. A little bit about our NanoResolution MRS 3D 2D sensor for wafer level and advanced packaging applications. In the NanoResolution MRS sensor, we are using multiple projectors and multiple cameras. In this case, you are seeing 3 imaging systems and projectors here. Specifications for the NanoResolution MRS sensor are shown here. We are using a field of view of 15 by 15 millimeter. The lateral resolution we are achieving is 3 micron. The vertical resolution we are getting is 0.05 micron. Our accuracy is half a micron. Our repeatability, 3 sigma repeatability is half a micron. The minimum lateral feature size we can measure is 25 micron. With that, the inspection rate we are getting is 75 million 3D data points a second. And finally, the last but not least, we can measure more than 25 300 millimeter wafers per hour using this technology right now. So how does the NanoResolution MRS sensor compare with conventional laser triangulation sensing technology? On the left hand side, you see in the NanoResolution MRS sensor, we can generate both 2D and 3D at the same time. The 2D image is the basic camera image. On the 3D side, we are generating the data with 36 images from 3 cameras at different directions. We are merging all the 2D to 3D data simultaneously to get one composite image. On the right hand side is conventional triangulation. It works, but we are getting this data with 2 different passes. In one pass you do 3D only, and in the second pass you do 2D data collection, and then you merge it together. So you get significant speed benefit with the NanoResolution MRS sensor. We use the NanoResolution MRS sensor in our WX3000 inspection and metrology system that is shown here. And you can find the specifications of that system that can be used for both 12-inch and 8-inch wafers on our website. It is essentially designed for wafer level bump pillar inspection. We can do 100% inspection with throughput greater than 25 wafers, 300 millimeters wafers per hour, 2 to 3 times faster than conventional technologies. We are capable of performing 3D and 2D metrology and inspection in a single pass. We are using our MRS sophisticated algorithms to reject spurious reflections from shiny mirror-like surfaces. The technology is scalable to 1.5 micron lateral and 0.025 micron vertical resolution. So how do you use our WX3000 to measure uniformity during the copper bumping process? The process flow is the same as what I had shown earlier, but now specifically you are using WX system to inspect before the photoresist is stripped. So how exactly does the physics work when we are doing that? This shows the schematic of the bump height before the photoresist is stripped. Typically the bump is smaller than the photoresist height. So light is coming and reflecting from both surfaces, both the photoresist as well as from the bump. The bump can be very reflective, in which case you are looking at the specular direction, but the bump can be diffuse, in which case you can look at the non-specular reflection. Photoresist is typically very reflective, so you are getting specular reflection, but photoresist is also semi-transparent, so light is penetrating the photoresist. Depending on the refractive index of the photoresist, we are measuring apparent thickness. There are some geometric limitations on where we can use this system. The photoresist has to be greater than 45 micron for this to work, as well as the bump has to be below the height of the photoresist. Assuming that to be the case, what we can do is inspect the bump height even when the photoresist is there, so long as the aspect ratio is greater than 2 to 1. That means so long as the height of the photoresist to the width of the bump is less than 2 to 1, we have enough geometric angle to get the light into the corner of the bump and can get diffuse reflection into our camera. So long as that works, we are able to measure the bump height before the photoresist is stripped. Even when there's a solder cap on top of it, in fact solder cap actually helps because it makes the bump very diffuse in nature, we can look at the height again with the same limitation though, so long as the aspect ratio is 2:1 or better. So how do the results compare with conventional technology? So on the left hand side is the data with nano-resolution MRS sensor. On the right hand side is interferometric data, very accurate but very slow data. So typically for an interferometer, that is the advantage of the nano-resolution MRS sensor and WX system. So what are the benefits with the additional speed you are getting? Now you can do 100% 3D inspection and metrology for wafer bumps. So why do it? If you are getting cluster effect, that typically tells you have some kind of an equipment or a process issue. If you are getting a repeating defect, that typically tells you have a mask or a reticle defect. From the bump height distribution on each wafer, you can identify the performance differences between different plating systems and individual plating cells. And finally, you can avoid probe card damage if you are inspecting the whole wafer and making sure all the bumps are correct. So there are significant advantages of doing 100% 3D inspection. So what's our technology roadmap? The bumps continue to get smaller, the pitch continues to get smaller. Given that backdrop, our current sensor and the system, we can do 50 nanometer Z resolution, 3 micron lateral resolution, pixel resolution, and we can measure bumps that are 25 micron or larger, whether they are shiny or diffuse, that's not a problem. For our next generation sensor and system, we are targeting 25 nanometer Z resolution, we are targeting 1.8 micron lateral resolution, and with that we will be able to measure less than 25 micron bump, typically 15 micron or above. We plan to release that sensor and inspection system in second quarter of 2023. So in summary, MRS sensor-based phase shift profilometry can provide accurate and repeatable measurements, typically 2 to 3 times faster than conventional technologies. MRS digital fringe projection technology provides unparalleled combination of speed and accuracy. We can get 100% inspection with throughput greater than 25 wafers per hour, 300 millimeter wafers per hour. We have the capability to perform both 3D and 2D metrology and inspection in a single pass. The technology is scalable to 1.8 micron lateral and 25 nanometer vertical resolution for next generation 15 micron and larger bumps, and that will be available in the second quarter of 2023. It's a unique sensor architecture with multiple projectors and cameras that we are using that can measure the photoresist thickness and bump height before the photoresist is stripped. Thank you for your attention. Unfortunately, I'm not there in the conference room as you can see, but Felice Chen from CyberOptics is there to take your questions and answer them. Thank you again.